Hi, my name is Steve Kendricks. I am the Senior Technical Product Manager for AWS Batch, and I'm here to talk to you today about how to run batch computing jobs on ECS through AWS Batch, right? And we like to say that, AWS Batch can support hundreds of thousands, if not millions of jobs on, on ECS through Batch. And the reason that we do that is because of the scalability and the elasticity of the cloud, and then also the capabilities that ECS has built for us underneath the hood to allow this sort of scalability to be built on top of them so easily, right? So I'm going to talk through what AWS Batch is for, how we view batch computing on AWS. And then I'll get into a little bit about how you might think, what you need to think about in terms of architecting for this sort of massive scale. Even if you aren't running today at that scale, you can still set yourself up for success by thinking about the right things at the right time. I'll talk a little bit about how to run on spot versus on demand, and talk about some of the exciting things that we have coming up and you might have already heard about a little bit. Let's talk about batch computing and why you need a batch scheduler. Right, we tend to think of things like batch, there's definitely many definitions, but a few things are asynchronous compute. They need special queuing. They need, the ability to have lifecycle maintenance handled for them. Generally, we're talking about running a lot of pieces of work on a set of compute, right? And there's often more work than is least readily available in the compute space. So you need something to handle that work for you, right? You need retries, you need dependencies, you need timeouts. Something needs to manage the queuing and job lifecycle. And this is slightly different than what you might think of than a workflow manager, and I'll discuss what those differences are. It's a tool specifically designed to manage your batch jobs for you, right? That's what a batch scheduler is, right? And that word scheduler can be loaded sometimes, but that's sort of what we are talking about when we discuss schedulers. A batch scheduler's purpose at the end of the day is to maximize utilization of available resources. In many cases, on premise, especially, utilization equals cost, right? And so that is kind of how the calculation runs. You have this fixed set of on-premise resources, and you need something to run your jobs at the highest utilization, because at the end of the day, right, you're not getting any more compute. You're not paying for those over and over again. Really, utilization equals the cost that is charged back to the user. The point is to do this as swiftly as possible, right? Maximize utilization as swiftly by running the jobs as swiftly as possible, while respecting user priority, right? So those are kind of the key things of what a batch scheduler priority is. But in the cloud, we have a few extra things that we have designed for, right? Flexible capacity of the cloud means that utilization isn't important in the end, right? As an end to itself, the way it might be in on-premise. Utilization is only a measurement for how we get to absolute cost, right? The important thing at the end of the day is how much it takes to run your workload. If utilization can be an important way to measure that, but it's not necessarily, right? If you have poor utilization but lower overall absolute cost, right, you would probably take that trade-off in most cases. Throughput also changes, right? Where how we would consider the story no longer becomes in the cloud. How do I maximize the resources that I already have that are fixed in size, generally speaking? How do I maximize those resources, and how do I consider throughput? In those cases, do I need sophisticated scheduling so that I can make sure that the cluster is fully utilized? Or can I add more low-cost resources and just simply keep adding resources and scale out the workload or the cluster in response to changing job needs? So that's kind of the questions that we ask. Scheduling techniques definitely absolutely have their place. I'm not saying utilization isn't important. What I am saying is that in the cloud, utilization, again, as I mentioned at the top of the slide, isn't the end goal in itself. It really is a measurement of how to get to absolute cost, right? And then handling cloud native concepts then becomes much more important because we have this additional lever, a better way to get to those distinctions, right? Why, we don't often see, if you're familiar with many on-premise schedulers such as Slurm or others, we see many of those have difficulty translating to the cloud. It's certainly not impossible. We have many customers successfully transitioning, but why is it difficult to do so? It's difficult because very often customers build things for a homogeneous and stable world, right? Even if some on-premise clusters have heterogeneous capacity, those are stable. They don't change. Very often you see people building workloads specifically for the capacity, right? So I know that I have this amount of capacity. I'm going to build my application so that it will properly utilize those resources, right? And so you have nice right sizing, or I shouldn't say nice right sizing, essentially forced right sizing of application to compute resource. In the cloud, workloads don't have that constraint. They can be extremely heterogeneous, right? You worry much more about the application, what the application needs, and a lot less about what the requirements specific compute is, right? You generally are going to tend to say, okay, I'm in the cloud, I'm going to force the compute to fit the needs of my application and not the other way around. Heterogeneous workloads and homogeneous capacity generally don't mix, and here's an example of why that might happen, right? Especially for some of these on-premise workloads, you have, these on-premise schedulers, you have what would be considered, they still think about things in a homogeneous way very often, right? Even if, again, on-premise, they might have access to a heterogeneous pool of capacity, they need to know what that capacity pool looks like ahead of time, right? They have to understand, okay, here are the set amount of machines that I have to work with. They're all registered into the cluster, right? I know what they are so that I can make decisions based on them. And so a cloud architect has some difficult choices when they need to move that application into the cloud. You have maybe a single tenancy model where you say, okay, I'm going to say, we're just going to scale out M5 24XL for all of our workloads. And on the left here, I'm showing, some CPU bound jobs, some memory bound jobs, and a mix of jobs, right? And so I'm going to run those in, but okay, that's great. These jobs, they're going to run, but what's going to happen is you're going to get fragmentation of the resources. The M524XL is a great machine, but it's not 100% right size for all workloads, right? Especially for some things like the CPU bound jobs, it may not all fit in. You're going to have to wait around for those jobs to exit. You might have to spin up additional capacity to just run those additional jobs, right? So that's one cluster. That's some of the defaults to having just a single cluster with a bunch of M524XLs. On the other hand, you may decide, okay, I'm going to take a multi-tenancy approach. I'm going to take a cluster with a Slurm instance, and I'll have C5 24XL, and then I'll have another Slurm instance that's running all the very memory bound jobs that's running R5 24XL. And then another cluster with a separate third thing, and I'm porting all of my mixed jobs, or maybe my not particularly bounded, although it might be obviously it's bounded in one way or another, but not particularly strongly bounded the way some jobs might be. And I'm going to run those on the M5. That's great, but now you have two problems. You have a lot more maintenance because now you have three clusters that are all running, and you have maybe, if you're using Spot in particular, a loss of Spot capacity, where those jobs now just can't run. The memory jobs, you would have traded lower utilization in order to run them, but now, because of this kind of multi-tenancy model, they just can't run, right? So that's some of the challenges that people have when trying to port things into the cloud. Right, so that's one of the major reasons why AWS Batch was built, was to think about things from a cloud native scale first. Right, AWS Batch can handle complex job dependencies and retries. It can handle synchronicity of jobs. It thinks about things from a cost-oriented perspective first, right? It will take your jobs. It will analyze the compute resources that are required to run those from a cost perspective and then a capacity perspective, and launch your resources. We have all of the file system integrations, or application or infrastructure, architecture, for example, integrations that you might expect. It scales massively. It scales to zero, again, in large part thanks to the capability of Amazon ECS, and it supports the traditional high performance applications that you would expect your distributed training jobs, right? So that's kind of the high level, why we built AWS Batch. I can give you a little bit of things, since we're talking about this at a higher scale. Our single largest cluster that ran, essentially a production workload, 1.24 million vCPUs for a single account. 500,000 is the number of simultaneous jobs that are running, right? Not even vCPUs, just jobs, pieces of work segregated view work that are running concurrently in an AWS batch environment, again, in a single account. And then also the ability to handle containers, very large containers, right? So we have some customers running 30 gigabyte large containers. If you know anything about the container world, and obviously, AWS Batch requires containers. 30 gigabytes is a very large container image, right? What you might not expect to be running. This customer for very good particular architectural reasons had to have a very large container image, and we had to build in a lot of support for that sort of workload into our container services because to meet the needs of these customers, right? So we have the capability to handle some of these largest workloads. Oh, and AWS Batch is free. You only pay for the resources that you use, right? The EC2 instances that we launch or the file systems that we launch on your behalf. Here's a list of customers that have had success with Batch, right? Whether it be from the Quantitative Biology Institute out of Tübingen, Germany, right? That is helping customers reduce research time by 50% through a number of customers doing EDA workloads, autonomous vehicle workloads, just image transformation workloads, essentially the scale of workloads that you would expect to find on the cloud are using AWS Batch to accelerate their workloads, to reduce process management, and to make it easy to just bring those workloads into the cloud and run them at scale, right? And here's an example of how you do that, right? Why, going back to that recommendation, that pattern that I introduced earlier, right, with how you might do it. So let's take a look at how Batch handle these workloads. Especially, right, these are pretty diverse workloads. A lot of them internal have, some of them were very large companies. They have internal customers that are running completely separate workloads, or maybe one side is doing machine learning training and the other side is doing inference and the others are doing data analysis or comparison on the machine learning workload, right? So how do we handle these, right? So let's say we got CPU bound, memory bound, maybe you might consider a GPU bound job or a mix of different resources. How does AWS Batch handle this? Well, we take a look at the queue. We say, okay, let's sort these out. We've got certain memory job bound jobs. We're going to launch certain resources for those capabilities. We got certain CPU bound jobs. We're going to launch certain resources for those jobs. We got a mix. We're going to pack those in, and we can also, ensure that we don't overscale for your jobs, right? So if we have a case where we've got 2 extra jobs, we are smart enough to say, listen, I'm going to launch these 24XL size jobs to make sure I get capacity. But then also, we're going to scale down. We're going to be smart about which instance sizes we run to make sure that we aren't scaling up over for what you need. Right? These are the sorts of things that we do for you. You don't need to worry about those. You just submit it. You submit us the work. We handle the scale up. We handle deciding which instances to launch based on your requirements, of course. And then you can also control us. And I'll talk a little bit about how to how we manage that in the service. But you can control the service. But this is the sort of capability that we have. It's all done for you. You don't need to worry about that. Just worry about your application and their requirements. Give those to us. Let us handle the scaling. But that's also not easy enough, right? And at the end of the day, I just mentioned, okay, sure, but all of these instances, they still require monitoring. They still require certain things that maybe we don't really want to think about. I don't want to think about my application image. I don't want to really think about VM isolation. Maybe if I've got two different users all submitting to the same queue because that's convenient, it's easy. I just want to throw those jobs into a queue, and I don't want to worry about having those jobs interacting with each other on the same host if they're from 2 different users, right? So or other things, right? Again, I just want things to be simple and easier. And Batch makes it easy, but couldn't it be easier? Well, pleased to introduce, as you may have seen earlier in reInvent, AWS Batch jobs for Fargate Compute. What this gives you is it gives you fully serverless batch computing, right? So AWS Fargate, being a serverless compute resource that is then launched by AWS Batch, which itself is a serverless queue construct at the end of the day, queue and scheduling construct. We then submit those jobs. All you do is from submit job, you just give us the requirements. we pick those up, run those tasks on Fargate Compute. AWS Fargate automatically right-sizes tasks to compute right within the available SKUs. There's over 50 SKUs in terms of vCPU and memory based submission parameters that you can submit to. It has Fargate Spot in terms of cost savings, and AWS Batch will handle the queuing, submission, and lifecycle management, including for Fargate Spot. Right. So here's a typical batch workload and how that would look like. Right. What happens is, let's say that there's something, ahead of time, you've got what we call a compute environment, which is where your compute resources live. It could be a Fargate compute environment, or it could be an EC2 compute environment. You've got a job queue, and usually that's there to, as a job to live when it's not getting run effectively, right? So that specifies your job's priority, and it can also be used to split out, different users from each other if you require that. And then ahead of time, you've also given us the, the roles and permission and the job definition, which is just a Docker image, and the parameters for that image. So let's take an example, right? We have the compute coming in, maybe something to like an S3 bucket, right? And an image transformation job is a good example of this, right? Compute comes in, that triggers a AWS Batch job. So we hit submit job, that triggers the AWS Batch job, in the job queue. So we say, okay, great, now there's a batch job. It's in this queue, it's got this priority, and the AWS Batch scheduler takes a look at that and says, okay, what are the job resources that this job has, and what resources do I need to launch into the compute environment to run that? It could be, for example, the user says, hey, just run this on Fargate, right? I want it to be simple. And so the scheduler says, okay, great, I'm going to send this off to Fargate to take care of it. And for people with certain specific requirements, they may find an EC2 best fits their needs. For example, if they want an ARM architecture or, currently a GPU job, we run that on a GPU instance on EC2. So the scheduler will say, okay, great, let me launch some instances into this compute environment and place the jobs on the task when that EC2 instance is available. Job runs, and we give you the kind of the lifecycle updates on where it is and the logging, and we send it back to the job finishes, probably writing back to S3. So that's, just a typical life cycle of a batch job. Let's take a look at how this runs on Fargate, right? So same thing, and this is just a slightly more complicated, slightly more sophisticated way to run. So in this example, what we have two job queues hooked up to two different compute environments. One is a Fargate compute environment. One is a Fargate Spot compute environment. So what you can do is you can set priorities through the queues to run on different compute environments. So you can say, okay, I've got my high priority queue. That's going to run on a Fargate compute environment first, and then any additional work that's in that queue can spill over into Fargate Spot, right? And so what happens is that you can set a cap on max vCPU, and you say, I only want 100 jobs to spin up in Fargate. So I'm going to set 100, and then the second thing I'm going to have, I only really need 100 jobs to be my super high priority. So those are going to be in the Fargate. Everything else is fault tolerant. It's really not that time sensitive. So I'm going to save 70% by running it in Fargate Spot. So I'm going to set that up. Batch will essentially manage this for you. As the jobs comes in, we're going to pull jobs out of that high priority queue first. We're going to say, great, we're going to send those off to the Fargate compute environment. We've hit 100 vCPUs worth of tasks or jobs in that compute environment. I'm going to start throwing them at Fargate Spot, right? And you can do the opposite. You can say, okay, I'm running... I'm going to run those low priority jobs, and I'm going to submit those to Fargate Spot first, right? Or maybe I only submit those to Fargate Spot. They don't get submitted to the on-demand queue or to the Fargate compute environment. Excuse me. They only run when there's capacity in the Fargate Spot compute environment, right? So that's effectively how you can kind of set up simple priorities and simple ways to handle things, and that's how you can control batch through using these different mechanisms, right? So I'll talk about a little bit of some, again, as I said before, some use cases still required EC2 compute, especially like these massive scale 100,000 million vCPU runs, right? Still at this time require EC2 to achieve that level of scalability. Some things to consider for massive scale, right? We have up here, and I'll be referencing this slide several times, is job submission, right? How am I going to get the amount of work that I have into the queue to run it? Number two is dependency and retries, right? Those jobs are sitting in the queue, they're waiting to run. Especially if you're using Spot, which is really valuable for those large capacity runs. Fargate Spot, or sorry, well, Fargate Spot as well. EC2 Spot, provides that capacity control for you to, that cost control, for you to enable these really large workloads at low cost, right? But that requires, you have some level of retry capability in case your job gets interrupted. And I'll explain how that works. Compute, right? What does the compute look like? And then for logging, how do you measure, these jobs? So we'll go into these, but I do kind of want to talk a little bit about some of the new features that we have before I dive all the way in. We recently launched just a few months ago the ability to specify custom log drivers, right? So we can support 7 different log drivers, such as obviously AWS logs, but Fluentd, Splunk are those among those supported now, or the ability to let you configure AWS log driver, like change the logging group name was a frequent request. We release support for shared memory and TempFS, swap space, secrets manager integration, and those are just a few of the configurations that we allow now. So, and that was just all in the past few months, right? So thinking about those things as you submit the jobs, obviously, need to have those. You can use what's called an array. So in order to submit the job, you can use what's called an array job to enable these kind of massive workloads. Those are good for tracking effectively as a way to aggregate jobs at a higher level, so it make it easier to specify dependencies. I'll specify how that works a little bit later when I talk about dependency tracking. But that's definitely one thing. Let's talk about compute for a second. How do I control the scaling and the resources? So again, we see a similar thing to what I was talking about with Fargate, but in this case, it's EC2, where you have different mechanisms to control EC2 resources. So in this case, we have one job queue, it's a high priority job queue that is hooked up to a on-demand compute environment and a Spot compute environment. As you can see in the slide, we definitely want to have the capability to use on demand if we need to, and spin up Fargate Spot for the additional extra. You don't have to have it this way. You could have both Spot. You could have, we give you the flexibility to do what you need to do. The difference is, again, we want to make sure that we give you those capabilities. So on the top there, you see, okay, here I can specify my instance type if I want, or I can just let Batch decide by specifying optimal, and Batch will give you the right mix of compute for your job workload needs. I can specify max vCPU or minimum vCPU if I want. I can set the desired vCPU. I can do a bunch of things. I can also set allocation strategy. And what the allocation strategy allows you to do is to say, okay, Batch, out of all the things that you have, right, I want you to figure, essentially allocation strategy allows you to set how do you think about capacity. With a best fit progressive capacity for on-demand, what that means is that we will launch you what we consider the best fit resources for your jobs. However, if there's, for whatever reason, you need to, maybe we haven't set up, there's an you have a limit on certain instances, right? Certain EC2 limits on your GPU instances, and you need to fall back to a different instance type. We will do that for you, right? We will automatically spin up an additional capacity, right? If we get an error. For example, with Spot, we have the Spot capacity optimized allocation strategy. What Spot capacity optimized does is it predicts capacity pools within Spot. Out of all the instances you give us, we're going to predict which one have the deepest capacity pool so that, we can give you the ones that we expect will have the lowest likelihood of getting interrupted. As time changes, of course, the capacity pool picture changes, so interruptions are still very possible. However, when we reallocate capacity, what we're going to do is we're going to reallocate. Let's say you get a small pool of instances gets interrupted, we're going to reallocate capacity into that other capacity pool so that we can, give you again what we consider to be at the current time the least likelihood, and based on predictions that we've made from past, from the historical data as well, on what's likely to be interrupted. So that's kind of how you set up. Again, there's many more ways to do this. We give you these sort of primitives, and you can set up according to what your job needs are. So, we move into there. We move into a little bit of what we can talk about for, we've got that compute set up. Let's talk about some retry capability. Again, I started talking about Spot. 2 months ago, we launched custom retry capability. What custom retry allows you to do is to control whether a batch retries on job failure. A great example of this is a Spot reclaim. So customers told us, hey, batches are wonderful. We like the ability to retry, but what happens is I want to use Spot, and I've got certain application failure modes that I really want to avoid retrying on over and over again. But in order to use Spot, I have to allow for retries, because if I get interrupted, the job still needs to run. I don't want it to just fail and quit. So what we launched was the ability to specify certain reason, exit codes, or status reason, based on Docker concepts. Again, that allows you to say, hey, listen, on this certain failure, for example, host EC2 instance is terminated, which might indicate a Spot reclaim, retry, but on a different status reason or exit code, don't retry, right? And so that will allow you to say, okay, I'm going to retry. Or maybe that this one error it means that the job is just never going to succeed, but on this other error, it may work on a retry. And so you can distinguish between those two now, right? So that's critically important when you're running jobs at large scale, because the number of jobs that are failing are very often much higher, for a variety of reasons. Spot reclaims, but also application errors. Users sometimes submit misconfigured jobs. You don't want those jobs, right? Every job that's getting submitted is essentially another one that might be blocking a correctly submitted job from running. You don't want those jobs to continuously retry, because especially if there's 10,000 of them all trying to retry for an application error that's just never going to run. So this is a capability that we launched to support those workloads. All right, and so we kind of talked about here, we talked about a little bit about from backwards order, right? We talked about logging, we talked about compute, we talked about dependencies, we talked about retries. I'm going to talk about job submission and dependencies at the same time, right? So array jobs, right? So I mentioned it at the beginning. Instead of maybe, we have the capability to run just single jobs that are just running by themselves. We have multi-node parallel jobs, which I'll talk about separately. But we also have the capability of an array job, right? Which is an array job is a concept that we use to run many copies of an application, for something like a parametric sweep or a Monte Carlo simulation, or a large collection, any job that's very similar, and maybe they have like one environment variable different, but many copies of that job. I can just submit this to Batch and say, Batch, I've got this environment variable, run 1,000 copies of this jobs, and this can be used to like iterate through rows in an S3 bucket or something like that, right? So makes it very easy for you to submit the jobs, and it makes it very easy for you to track the jobs, because we have this concept of the parent job and the children job. The parent job is essentially the overall tracking mechanism and the dependency mechanism, whereas the children job run independently and can run in different forms of compute, and that helps speed throughput. So here's an example of a dependency model that you might have. We have job, depends on array job, right? So we have job B that's submitted. All of these are submitted at the same time. We have job B that's submitted. It's waiting for the array job A, to run. That's going to, run through its progression, all 100 jobs there, and then job B runs. You can do the opposite, of course, where maybe job A is a setup job, and then the 100 jobs in job B runs as well. You can do end-to-end dependency. So you're going to submit 2 array jobs, and you'll say, okay, I'm going to run through all of my jobs, and make sure that job A0 runs, then job B0, doesn't run until job A0 finishes. And then you can do it depends on self, which is A0 runs, and then A1 runs, and then A2 runs, right? So you can combine these together to have multiple different mechanisms. Um, for example, maybe I have, as I mentioned before, you've got some workflows are very complex. They have different steps, different processes that need to happen. You've got setup, you've got, in this example, heavy IO, CPU intensive, large memory analysis reporting. You might have a GPU intensive step in there. And what Batch allows you to do, through these very large workloads is to set up and say, okay, I'm going to run, all of these. I think I've got, 20,013, 14 in here, jobs. I'm going to submit them all at the same time, right, through 4 API calls, 5 API calls, right, to submit job. Batch is going to iterate through these, track and build a little dependency graph and run the right compute for the right steps. So in this case, the only thing that's going to run first is a setup job. That's going to run on its own. We don't spin up any other capacity until that job runs. Once that job is done, we're going to look at the heavy network IO step and say, okay, these jobs now are ready to run. What's the capacity that we need to effectively run these jobs? I don't want to look at the large memory yet. I can't run the large memory yet, so I don't want to waste the customer's money to spin those up. We're going to take a look at that. We're going to spin up and say, okay, great. Job B is a depends on self. It's going to run through all of its progressions first. Once that step is done, we're going to do two things. We're going to take a look and we're going to say, okay, great. Job C and job D are end-to-end dependencies. Let's look at both of these effectively, right? Not quite in the same order because some jobs in job C need to run first, but let's take a look at job C. Are the same resources that I have to run the heavy network IO, can those run the CPU intensive jobs? If so, I'm going to keep those around and start running the CPU intensive jobs. If they can't run them, then I'm going to shut down the heavy network, the instances I spun up for heavy network IO, spin up new compute to run the CPU intensive jobs, run those. Once those start to finish, I'm going to start progressively spinning up instances for large memory, assuming that those need different instance requirements. For example, right, we see that C0 can run and then D0 can run. D0 only needs to wait for C0. It doesn't need to wait for C9999 to run. It can only it can run when it's ready. We'll spin up the capacity for that job if needed at the time that it's needed, right? You don't have to manage any of that. When the job is ready to run, we'll spin up compute for it, assuming that we don't have something to run it already. When we don't need it anymore, we shut down that instance automatically for you. You don't need to run it anymore, right? So that's the sort of thing that Batch does for you. That's an easy, quick, fast, and dirty explanation to setting up to run jobs at massive scale. Again, this example is something like, if I did my quick, fast math correctly, is something like 20,014 jobs. We can support many more jobs than that, as I explained earlier. A question that I get asked sometime, kind of in closing, is, okay, that's great, but isn't that capability, we start talking about dependencies, isn't that capability similar to what we have in AWS Batch, in a workflow manager, right? And that's true. Some of those concepts and terms are familiar, right? And matter of fact, Batch is a great integration with workflow managers. We have many workflow managers that use Batch either as, if you want to use the Airflow terminology, as an executor and operator. In some cases, AWS Batch is the compute layer. Well, what's the difference? So the main difference between what we consider a workflow manager and a batch scheduler is, workflow managers are great if you need to schedule across different services, right? So, for example, Step Functions has great interaction with AWS Batch, and it has also great interaction with SageMaker or Kinesis or ECR, and it's great for those sorts of mechanisms where you need to schedule different jobs to run on, maybe the first process it needs to submit its work to, it needs to upload a new container to ECR, and then it needs to run some data through SageMaker to train a model real quick, and then it's going to run those over for large scale testing in AWS Batch, right? That's a great way to utilize a workflow manager. Something like Nextflow, which has amazing interaction with AWS Batch, or Metaflow, is built using, very much relying on AWS Batch as one of the primary compute orchestrators, especially on AWS. we'll have other data pre-processing steps, certain ways to set up a pipeline, right? Those are great ways for great uses for workload managers, but AWS Batch is really meant to be that decision maker when it comes time for compute about what resources get run, how to spin those up for you so you don't need to worry about them, and how to run those in the most cost effective, considering absolute cost, in the most cost effective way possible for you, right? And that's why all of these workflow managers integrate with AWS Batch. So that's a overview of how AWS Batch works at scale. If you have any questions, please don't hesitate to reach out to the community, or I put my name up there at the beginning of the slide. It's Steve Kendricks. Please feel free to look me up and ask questions. Thank you very much for joining us. I know it's a little bit different this year, but it was great talking to you all, and happy to answer any questions in the chat. And don't forget to fill out the session survey.